So in this one, we're going to look at part of the derivation for equilibrium. Consider a system like this that's not at equilibrium at the beginning, and it's partitioned, and these 1 and 2 represent the two phases of the material in this system. Just thought experiment. So we have side 1, we have side 2, and each side has an amount of entropy, number of moles, and then there is exchange of material into these two parts of the system. One thing that we're going to make use of is we're going to make entropy as a function of internal energy, volume, and the number of moles in each phase. So S1, U1, V1, N1, just so that we can take a look at the derivatives and then get a relationship for how we reach equilibrium. Unfortunately, there's one small part of this that was a little bit beyond what this course covered because we didn't go too deep into Maxwell relations and all of the thermodynamic transformations between the different variables. So there's going to be one point on this little derivation where you're just gonna have to do some more digging to find out on your own, or just accept the information as is. So if we have entropy, for instance, in partition 1 of this system, we want to know how that changes. So we can write ds partition 1 is equal to, well, it's for any type of system, it's going to be equal to how much this changes with respect to u with constant v1 n1 times a small change in u, plus look at how the system changes with respect to the volume. This is just taking any type of variable or any type of function and then just breaking it into its small pieces and understanding how the whole changes as the sum of the small parts. Something by this point in the course everybody has been having a lot of practice with. So these are partial derivatives with respect to u times a small change in u. Partial derivative with respect to v, small change in v, plus a partial derivative with respect to the number of moles times the small change in that number of moles. Of course, here we're going to have u and v being held the constant for that derivative. The part that can be shown, and I have a video that shows part of this, is that this term here is equivalent to 1 over temperature 1. This term over here is equivalent to pressure 1 over temperature 1. Okay. And then this term here is the Gibbs free energy in 1. Partial molar Gibbs free energy in 1 over the temperature in 1 times the small change number of moles there. So we can rewrite this whole equation as 1 over T1 ds 1, not ds1, du1 plus the P1 over T1 times dV1, okay, minus G1 over T1 dN1. In all of our relations, whenever you see dN1, a change in the number of moles of one of the components, it has to do with chemical potential or actually the partial molar Gibbs free energy. If it's a pure component, then the partial molar Gibbs free energy is the pure component Gibbs free energy. And in this course, we are only doing pure component Gibbs free energies. So here, those would be synonymous. But recall, this is for 1/2 of the system. What we have is a couple more pieces of information. In the total system, this is equal to ds1 plus ds2. Do you agree? Okay, so if we do this, we can use our substitutions from above to rewrite this equation. 1 over temperature 1 du1 plus 1 over temperature 2 du2 plus P1 over temperature 1 dV1 plus P2 all over T2 dV2 minus GI over T1 times dN1 minus G2 underbar over T2 dN2. But because this is a closed system, and the summation is a closed system, we have one more simplification. The change in the number of moles that goes in system 1 is equal to the opposite of what's happening in partition 2. du, the energy that's, because it's a conserved quantity, lost in one is what is going to be gained in the other. And the same thing with any type of change in the volume that this partition is going to occupy. Any loss in one is going to result in the gain of the other. And so if you make these substitutions for the fact that this is one composite closed system, we end up with this really interesting relationship. Okay, ds equals 1 over temperature 1 in partition 1 minus 1 over temperature 2. Okay, times du1. Okay, plus P1 over T1 minus P2 over T2 times dV1. We're using these relationships to substitute out the one of the two changes. Then lastly, minus Gibbs free energy 1 for T1 minus Gibbs free energy 2 over temperature 2 times dN1 for that relationship. Okay. So what's interesting about this is that at equilibrium, ds equals 0. Because S hits a maximum. That's just what S does. Now, we know in this system that for this to take place, these can vary independently of each other, but by process of elimination, we'll start with this one. At equilibrium, ds is equal to 0, and so there's the independent variables u and v and n that also will be approaching some equilibrium level at that point. But there's two ways of having equilibrium here. You can have all of these equal to 0, or you can have all of these terms equal to 0. You can have all of these terms equal to 0. And so one way to ensure that ds is equal to 0 is if each one of these, independently of all the other things that are going on in the system, are equal to 0. So if we just force 1 over temperature 1 minus 1 over temperature 2 to be equal to 0, this gives us temperature 1 equals temperature 2. Of course, at equilibrium, this is intuition, the temperature in the two partitions, the two phases in this example, they're going to be equal. If there isn't equality in those two partitions, then there's going to be a temperature gradient. When there's a temperature gradient, there's going to be a flow of energy. So that one makes sense. Then if you use this one on this one, you'll find that P1 over T1 has to be equal to P2 over, we can make the substitution, T2, or just call it T1 since T1 equals T2. So then P1 has to be equal to the pressure in system 2. Also, this makes sense if you think about the system as closed. If there was one part of it that had more pressure than the other and there was free exchange, of course, your intuition says, well, that's not stable. It's going to change until the pressures are equal. Now, lastly, we can do the exact same thing that we did for pressure to show that partial molar Gibbs free energies of the two phases, or for a single component, this is the per molar Gibbs free energies. The two partitions, which happens to be the two phases, must be equal. This is the criterion that we ultimately will focus on calculating for determining vapor-liquid equilibrium.